Hey there, and welcome to the final video for Chem 120 with me. This is for Chapter 8, Part 2. And what we're going to be looking at in this video is we're going to be looking at Lewis structures that do not, Lewis structures that do not obey the octet rule, resonance and formal charge, and geometry, okay? And there's two pieces to geometry. So first of all, we're going to be looking at Lewis structures that do not obey the octet rule. This will be very important, okay? And then there's resonance and formal charge, and then two kinds of geometry, electron arrangement and molecule shape. Okay, so these things are all going to be on your final exam, and they're all going to be a part of the one-on-one Zoom meeting that you do with me if you're taking this online. Okay, so first of all, let's look at Lewis structures that do not obey the octet rule. And there's a couple of times that that's going to happen. And so grab a periodic table and take a look at your periodic table. Okay, and I've got mine here. Okay, so now if you look at this, you can see it up there. You see how boron is there and beryllium is there. Let's take a look at just boron and beryllium for a moment. They're very small. Okay, so lithium, this is just continuing on from last week. Lithium is an alkali metal and it will always form ions, never molecules. Beryllium is a little bit different. It's sort of half ionic, half covalent, okay, or polar covalent, very polar covalent. And boron is always covalent. Call this half. Okay, so remember in ionic bonds, you're actually doing a full give and take of electrons. Boron is always covalent. And sometimes it's polar, sometimes it's not. Now, beryllium, if you remember this from last video, beryllium has 1, 2 valence electrons. It only has 2. And boron has 1, 2, 3 valence electrons. And carbon, just for argument's sake, has 1, 2, 3, 4 valence electrons. Well, you remember from last week that means for carbon that there are 4 places for bonding. Now, if we look here, beryllium, I suppose you could add 6, but for a very, very tiny atom like beryllium, beryllium is number 4 on the periodic table, so it only has 4 protons. To add 6 electrons around beryllium would be a lot. It would be too much for the beryllium nucleus. Boron only has 5 protons. And it doesn't have a dot here to offer. It doesn't have another electron to offer. So what you'll find with this is that beryllium is happy with only 4 electrons around it, okay, in its valence, and boron is happy with only 3. Now, sometimes boron will follow the octet rule and sometimes it won't, okay? So first of all, carbon will always follow the octet rule. And what that means is that carbon will almost always have 4 bonds. And in those 4 bonds, you know that we have 8 electrons, okay? However, if we come over here and look at beryllium and boron, because they're not here, sometimes beryllium and boron will follow the octet rule, but sometimes it will not. So we'll say sometimes but sometimes it'll be happy. So carbon will always follow the octet rule, so it have 8 electrons around it. Sometimes beryllium will be happy with only 4 electrons in bonds. And sometimes boron will be happy with only 6 electrons in bonds. And the reason for that is that their nuclei are very, very small, that they're and that they're very close to helium. Carbon is halfway to neon, so it always follows the octet rule. So other things that always follow the octet rule will be nitrogen, oxygen, and fluorine. All right. So that actually brings me, before I get to the next part of not obeying the octet rule, let's talk about a couple of alwayses. Okay, ready? Let's review this. Always rules in Lewis structures. I would write this down so that you have it handy. All right. 1, hydrogen will always have 1 bond. It will never have 2 or more bonds. Oh, let me just leave it. It will never have 2 bonds or lone pairs. Never, never. Ever, ever. The second always rule in Lewis structures is that fluorine will always have 1 bond and 3 lone pairs. Okay, it'll never have anything else. Fluorine will never double bond. It'll never exceed its octet. It will always look like this in everything, from diatomic fluorine gas to hydrofluoric acid to carbon tetrafluoride. Always, 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 it will look exactly like this. Okay, so now let's look at our second set where we have atoms that exceed the octet rule, all right, or atoms with expanded octets. And the slides talk about this more in detail. All of the atoms that I'm going to put up here can expand their octets, but they will often obey the octet rule as well. So you have to take them in a case-by-case basis. Okay, so atoms with expanded octets, first of all, they have to be 3rd row or higher. Okay, and instead of 3rd row, let's say energy level N equal to 3 or higher. So 4th, 5th, 6th, okay? They will never be at lower energy levels than that, okay? And the reason for this is that energy level 3 is the first energy level with d orbitals. So every atom in row 3 and larger has d orbitals that it's not using. Okay, for example, if you look at, say, phosphorus, okay, phosphorus is in the 3rd row, it's number 15. I'm looking at my periodic table while I say this, okay, and if you'll remember, so phosphorus, number 15, okay, and it has 1s2, 2s2, 2p6, and then we have 3s2, 3p3, and that's its electron configuration, okay? So we know that these are our core electrons, okay? And then these here are our valence electrons. Now 3s, 3p, we're not going to fill the 3d orbitals until the next row after the 4s orbitals, which means that phosphorus has its level 3 orbitals right there and empty. And so extra electrons can be put there to when necessary. Okay, so let's take a look at an example for that. Sorry. All right. Okay. I wanna do one that, okay, I'm not sure if you can already see this one, but we'll try. Okay, so let's look at phosphorus while we're working on this, and we'll say, okay, let's look specifically at PCl5. Okay, and let's walk our way through that in the same way that we did last week or last video if you're watching these close together. So phosphorus, we know, has, okay, so first of all, let's go ahead and review here. Phosphorus has 5 valence electrons, 1, 2, 3, 4, and we'll put one here, 5. Okay, and chlorine has 7, 1, 2, 3, 4, 5, 6, 7. Okay, now here's a good trick. Chlorine can also expand its octet. And you're going to see that in your recitation, and you're going to see that in your homework. If chlorine is placed with something that is more electronegative, like fluorine, chlorine can expand its octet and become a central atom. It's not real common, but it definitely happens. You'll also see it in polyatomic ions, like the chlorine ions, like chlorate, chlorite, those. So you have ClO, ClO2, ClO3, ClO4, and you'll get expanded octets on your chlorine in that case as well. Okay, now in this case, we have 5 of these, okay? So what we're gonna do is we're gonna say, okay, well, this forms one bond, and then this one can form a bond, and this one can form a bond, and these both can form bonds in this case, okay? And so let's go ahead and count our valence electrons. So phosphorus has 5 and chlorine has 7, 5 each. So that's 40 electrons. Okay, and let's begin organizing this. So first of all, we have phosphorus. And we have 5 chlorines. So we're going to arrange them all like this. And now we're going to count our bonds. 2, 4, 6, 8, 10. We have 5 bonds with 10 electrons in them. Okay, now let's put the lone pairs on chlorine, and then we'll count again. Okay, now I have made 5 times 6, or I've made 30 dots. Those are my lone pair electrons. And then I have 10 electrons in bonds, so 40. So I have counted on this 40 electrons. Always count your electrons, especially when you're doing double bonds or expanded octets, to make sure that you don't have too many or too few. That's really, really important. Okay, so at this point, I'm actually also going to start talking a little bit about formal charge and why it's important, because the book sort of puts it in, but it's more important than just a little bit here and there. Excuse me. Okay, so let's take a look at PCl5, this Lewis structure that we have drawn. Formal charge looks at the burden of negative charge that an atom is carrying, okay? Formal charge of 0 is best, okay? So I'm actually going to put that here, okay? Formal charge at or close to 0 is best. Okay, now the way you find formal charge, let's call this FC for formal charge, is that you take the number of valence electrons and you subtract the number of bonds, and then you subtract the number of lone pair electrons, okay? So let's start here by looking at the formal charge here for phosphorus, right here. Phosphorus comes with 5 valence electrons from the periodic table. If you don't remember how to find that, you can watch last week's video and it will go over that again. But basically you just start on the left and count the S and P electrons until you get to your atom. Now here attached to it, it has 1, 2, 3, 4, 5 bonds, minus 5 bonds. There are no lone pair electrons on this phosphorus. Therefore, the formal charge on the phosphorus is 0. Perfect. Okay, now let's look at the chlorine. Now, all of these chlorines are what we call chemically identical. They all have 1 bond and 6 lone pair electrons. Because they're all chemically identical, we can look at only one of them and we'll say that all of the formal charges for the chlorines then are the same. Sometimes you'll have 2, like for example, 2 oxygens in a molecule and they're not chemically equivalent. One of them has a double bond, one of them has a single bond, so you have to treat them separately. But in this case, they are all chemically equivalent. So let's go ahead and we're going to look at this chlorine right here. This chlorine comes with 7 valence electrons. It has 1 bond on it, and it has 1, 2, 3, 4, 5, 6 lone pair electrons, minus 6 LPEs. 7 minus 1 minus 6 is 0. So the chlorine also has a formal charge of 0. The fact that all of the atoms in this molecule have a formal charge of 0 means that this molecule, that the way we have drawn it is correct and it is stable. Okay, let's look at a couple of others. Let's take a look at sulfur tetrafluoride. With sulfur tetrafluoride, SF4, okay, let's begin by counting our valence electrons, okay? Sulfur comes with 6, fluorine comes with 7, and there are 4 of them. So 7 times 4 is 28, plus 6 is 34. Now, let's remember, if you don't have to draw the individual Lewis dot structures for the individual atom, that's fine. I'm doing it here so that you can see where everything comes from. Okay, so let's go ahead and remember our sulfur with 6 valence electrons is going to look like this. Okay, and let's remember our fluorine. 1, 2, 3, 4, 5, 6, 7. Okay, now technically speaking, when we look at this, we see that fluorine has this 1 spot for bonding and sulfur has 1, 2 spots for bonding. Okay, well, but we have SF4. We cannot put any double bonds on fluorine. It cannot double bond. It cannot bond to 2 things. Fluorine will never expand its octet. It will always have 1 bond right here on this square with this unpaired electron and these electrons here. That's never going to change. So in this case, we're going to put sulfur in the center and see what more we get from it. Okay, so let's bond like this and we'll put the 4 fluorines around it. 1, 2, 3, 4. Now, we've already mentioned that fluorine will always have 6 lone pair electrons. So we're going to draw those. When you get to organic chemistry, you'll find that sometimes they don't draw all these dots. Okay. However, in general chemistry, you will draw the dots. It's important to know where those lone pair electrons are. And so without the dots, I will assume that you did not, I will not assume that you knew that they should be there. Okay. So they need to be there for the molecule to be correct. So now let's take a look at this. Okay. So if we look, we have 6 times 4, we have 24 lone pair electrons on the fluorine. Okay. And we have 8 electrons in bonds. And that means that so far we have 32 electrons. but we need 34. So the question is, where are we going to put that last lone pair? In this case, sulfur is going to expand its octet and we're going to put that last lone pair right there on the sulfur. Okay, now let's take a look at those formal charges to see how this looks, to see if this molecule is stable. Whenever we do something weird like this, it's really important to look at the formal charges. Each fluorine, we'll start with the fluorines, each fluorine is chemically equivalent. They are all identical, 1 bond, 6. Okay, so for the fluorine, they come with 7 valence electrons, minus 1 bond, minus 6 lone pair electrons for a formal charge of 0. So our fluorines are stable. Now let's take a look at our sulfur here in the center. Okay, now the sulfur comes with 6 valence electrons, minus 4 bonds, minus 2 lone pair electrons, and we can see that that means that sulfur is also stable because it has a formal charge of 0. Okay, and I'll say equals formal charge right here. So this checking of our formal charges is what is going to allow us to determine if a molecule or a polyatomic ion is correct when we do something odd to it. Okay, all right. So now continuing with formal charges, let's take a look at resonance structures. Okay, so in the slides, we have a couple of slides that deal with the nitrate anion. Okay, you can look at the slides for that. I want to walk through another process and resonance and formal charge. Okay, we'll continue formal charge here. Resonance doesn't happen all the time, but it almost always happens when you have a polyatomic anion. And that's because you've added an extra electron or 2 or even 3 onto a molecule, and those extra electrons can move basically around the molecule. And a polyatomic anion is just a molecule with extra electrons stuck onto it. Okay, so let's take a look at OCN minus. Okay, let's take a look at this anion. First of all, let's go ahead and set things up a little bit. So our oxygen has 6 valence electrons. Our carbon has 4 valence electrons. Our nitrogen has 5 valence electrons, and this negative charge here is another 1. So now if I look at this, I see that I have 16 electrons that are going to be accounted for in our ion. Okay, now let's just go ahead and remember that our oxygen looks like this, that our carbon looks like this, and that our nitrogen will look like this. Now, a really important thing to remember when we're doing this is that oxygen, carbon, and nitrogen are all row 2 elements, and none of them can expand their octets ever. So that we can't, whatever we do here, we have to do with double bonds, not with octet expansion. Okay, so let's go ahead and arrange these. And I'm going to arrange them exactly as it's written. That's usually the safest way to do this. And that'll work too, because it's going to put the carbon in the center, which is good because it's the least electronegative of the 3 atoms. And usually your center atom will be the least electronegative. That changes a little bit in things like water, but that's often the case. So let's go ahead and arrange it. We have O, C, and N. Now we're going to be remembering that this is, and actually I'm going to erase this because we're going to need some more space. Okay, there we go. Now you'll notice that I have these brackets around it. in order to identify that this is not a molecule, it is an ion, you have to put the brackets and the sign on the outside here. Okay, now let's take a look at what we've got here. Now I've got 4 electrons accounted for. I need to account for 12 more. So let's go ahead and start placing them. Well, here's 2, 4, 6, 8, 10, 12. Okay, now I have 16 electrons in here, but my carbon is not stable because it only has 4 electrons around it. So what am I going to do? Well, there are actually more than one thing that I could do. So, but what I'm going to start with doing is I'm going to start with moving in a lone pair from each side and creating 2 double bonds. Okay, so what will that look like? Okay, so I'm just going to go ahead and take this out like that. And I'm going to keep the, now I'll just go ahead, there we go. Okay, so now I have 16 electrons accounted for, and I need to do formal charges here to determine whether or not my drawing is going to be stable. So let's go ahead first, and I'm going to keep kind of a color scheme going here. Let's look at carbon. Okay, the carbon has 4 valence electrons, and in this case, it has 4 bonds. So it has a formal charge of 0. Okay, now let's look at the oxygen that I have drawn here. The oxygen comes with 6 valence electrons. It has 2 bonds on it, and it has 4 lone pair electrons on it. That gives it a formal charge of -1. Okay, so let's begin by identifying. Okay, there we go. We have a formal charge of -1 there. Okay, and now let's look at our nitrogen right here. Okay, nitrogen comes with 5 valence electrons. Here it has 2 bonds, and it has 4 lone pair electrons. Okay, oh, whoops, wait, go back. Sorry about that. I was thinking ahead and I didn't mean to do that. 6 minus 4 minus 2 is equal to 0. Okay, so here my oxygen is 0. I was thinking ahead to the next structure. Okay, and now though we have 5 minus 2 minus 4, and that gives us -1 on the nitrogen. Okay, and oh, I think I lost my negative sign. There we go. Okay, and you'll notice that that this -1 here matches this. So this is a good Lewis structure. We have to have a -1 in our formal charges somewhere because the formal charges have to add up to the charge of the molecule or the ion. So this is pretty good. But let's take a look at what happens when we move the formal charge. Now, the formal charge of -1 is probably not going to lie on the carbon. Carbon is very kind of electroneutral in a way. Its electronegativity is right around 2, and that's halfway between high and low. It's not going to tend to hold that negative charge. And right now it's on the nitrogen. So what we want to do is we actually want to put more of the lone pair burden on the oxygen. And the way we could do that is we could say, okay, well, we have 4 bonds here. One thing that we could do is we could single bond the oxygen to the carbon, triple bond it to the nitrogen. And we know from ammonia and N2, nitrogen gas, that nitrogen likes to be triple bonded. So this isn't totally legit. What we're basically doing with this is we're taking this bond and we're moving to the oxygen, and we're moving this lone pair in like that. Okay, so now we have 2, 4, 6, 8. Carbon is stable. We're going to leave that lone pair on nitrogen. 2, 4, 6, 8 on nitrogen is stable. And what we have accounted for, we have 10. So we need to put 6 more electrons on the oxygen like so. Now, if you take a look at this, and again, we have to have those brackets with the negative sign because it's an ion. Okay, now let's take a look at this and let's look at those formal charges again. Okay, for the carbon hasn't changed. The carbon still has a formal charge equal to, still has a formal charge equal to 0. It hasn't changed. It still has 4 bonds on it. Okay, now let's take a look at the oxygen that we have right here. And now the oxygen started with 6. It has 1 bond and 6 lone pair electrons, which gives it a formal charge of -1. And there's the formal charge of -1 that's going to match my overall charge. And now last, again, we have that nitrogen, and nitrogen comes with 5 minus 3 bonds minus 2 lone pair electrons, and that gives it a formal charge of 0. So what we've done between here is in the first resonance structure, our nitrogen has extra electrons on it, so to speak. It has more of an electronic burden. And the second one, the oxygen has more of an electronic burden. Which one is correct? Well, the answer is both of them. And that's the point of resonance, is what we see is that the electrons from this bond and this lone pair are moving. And you're going to see this very, very rapid movement between the two. So rapid that it's almost like they're both happening at the same time. Because remember, electrons are very, very tiny and extremely fast. And when something is that small and that fast, it's almost like it's happening simultaneously in simultaneous locations. And that's what our resonance is. Okay. Now let's take a look at our last piece of information tonight. And again, please spend some time going over the slides and the text. So tonight, the last thing that we're going to take a look at is we're going to take a look at VSEPR. Valence shell electron pair repulsion. Okay. Now, what this is really looking at is this is looking at geometry. Okay, and geometry is going to have 2 pieces. First of all, the slides begin by looking at geometry with no lone pairs. Okay, so if there are no lone pairs on the central atom, then the geometry of the electron arrangement equals the geometry of the shape. So we could say geometry of electron arrangement equals geometry or shape of molecule. Okay, so this is all in your slides, but I'm going to show you some models that go with it. First of all, you can just look in the little picture of me that's up there. First of all, you can see something like this. This is like maybe beryllium chloride, but there's 1 central atom and 2 and 2 side atoms here. Okay, in this one, okay, so I'm just going to put over here what I'm working on at the time. There we go. Okay, this molecule is linear. And this bond angle on the central atom is 180 degrees. Okay, and that's how it might look. Now, again, if you're thinking, where's she getting this from? I want you to stop. I want you to go find the slides, and I want you to do this section of it either with the printed slides or with notes in front of you, or maybe with the slides on your phone while you watch this on your computer. But stop, go find the slides and have them up while we're looking at this. What I'm doing is I'm literally going through the slides and showing you examples. Okay, so this is that linear arrangement that we start with. I have a box of models that I put together here. All right. Okay, now the next one that we have here to look at is is a, let me find it. Ah, okay. The next one that we have here, I want to make sure I go in the same order as what's in your slides. Trigonal planar. And it's like that because, let's take a look at what we have. Tri means 3, and planar means basically in the plane. Okay, so this isn't really a 3-dimensional molecule. See, all 3 of them are in the plane and they make this. So what they're doing is, remember, valence shell electron pair repulsion. The geometry is based on the molecule's electrons being as far apart as possible. Okay, so again, here we have, I'm trying to show this really well. Now everything's mirror image and it's tricky. Okay, so here we have trigonal planar, and the bond angle for that is 120 degrees. Let's see what's next. I have, on purpose, I have 3 different molecular model kits in here. And the reason for that is because I think it's really good for you to see these different, they're all ball and stick models of one kind or another. Okay. Now, the next one that we go to as we're working our way through the slides. Actually, hang on. Let me stop the share and I'll just go to the slides. There we go. That was a brilliant idea. Okay, there we go. It's a little easier. Okay, so again, that first one that I showed here was linear, and here's a picture of what the model might look like. Okay, and then the next one that I showed was this trigonal planar. Okay. Okay. Nope. Okay, and now the next slide here shows tetrahedral. Okay, so go ahead, take a look at how this is. You can see the tetrahedron here. Okay, it forms this 4-sided thing, okay, with an atom in the center, a center atom. And one example for that might be methane. And just notice here, they're all 109.5. That's our bond angle. Whoops, 109.5 degrees for a bond angle. Okay, now let's take a look at the next slide that I have here. Okay, so remember, this was tetrahedral. Now let me actually come back here for a minute. In this tetrahedral molecule, what you have is the tetrahedral equals the electron arrangement and the molecule shape. And that's because we don't have, sorry, we don't have any lone pair electrons. We have bonded atoms on every place that's available on that carbon. Okay, now what happens though if we take a look here at our tetrahedral electron arrangement? Okay, so now we have tetrahedral electron arrangements. But what we see here is what happens if we replace them. I'm trying to see what I have here. Okay, so let's take a look. First of all, if we were to take off one of these, now we have ammonia. Okay, and we just have a lone pair up there. I have paddles on the other ones to show my lone pairs, but you can imagine it. Now in this case, we still have a tetrahedral electron arrangement, okay? We still have something at least close to that 109.5 bond angle, but we don't have an extra atom up there. And what that means is that the molecule shape of ammonia is trigonal pyramid. So in this case, you would write two separate things. The electron arrangement is tetrahedral, the shape is trigonal pyramid. Now let's take a look at what happens when we replace two of our, my bonds are there. When we replace two of them with lone pairs, and in this case, I actually have paddles in place, okay? This is an example of water. H2O, okay? And the shape of water is V-shaped. Sometimes I see it called V-shaped. Sometimes I see it called bent. So you'll see it listed as both. They are both correct. Okay. The electron arrangement, because you can see these lone pairs up here, is still tetrahedral. And in part that's because these lone pairs, these two electrons actually take up more space than the hydrogens down here do, because they have a large negative electron cloud for each one of these, okay? And they're not localized, okay? All right. Okay, now let's take a look at the next possibility. Hopefully you guys can see this okay as I'm going through it in my little screen. Okay, the next, now we're working forward and we're looking at some expanded octets. Okay, so we're looking at expanded octets. And for both of these, okay, we have no lone pairs. So that means that the designation trigonal bipyramid in this case is the shape and the electron arrangement. And that's true for both of these. Okay, so let me see if I can find, okay. So here you can see in this little model that I have one thing here, my central atom, and then I have 5 more, okay? And here you can see that I have 2 here, straight up and down. Then I have 1, 2, 3 in the plane, okay? And that's a trigonal bipyramid. Now in a trigonal bipyramid, let's take a look at our bond angles. Here we have a bond angle of 90 degrees. And then in our, with the 3, so if we come across like this, so the ones that are in the 3, so 1, 2, 3, the triangle are 120 degrees. And then the 2 up and down are 180 degrees or 90 degrees from the triangular pieces. Okay. Now, if we looked at octahedral, each one of the octahedral sets here, like this, or here, they are all 90 degrees from each other. Every single one here, 90 or 180, I suppose, if you wanted to come all the way around. So everything is between 90 and 180. Okay, and now this is an example of an octahedral molecule. Okay, and you can see no matter how you look at it, you have that 4-way kind of box with 2 off the side, and that's an octahedral. Oh, sorry. Okay. Oh. Okay. Now this is just a review for this slide, actually. Okay. So let's take a look at what happens in this slide. And I'm actually going to, hang on a second. I want to make this bigger. Okay, now it's a little easier to see this. Okay, so let's take a look at what happens with some of these when we put lone pairs on the central. So you've already seen this one, the tetrahedral becomes a trigonal pyramid or V-shaped bent. And this is the molecule shape is here. And the all the electron pair arrangements are all tetrahedral. Okay, now let's come over here. Okay, all of our electron arrangements are going to be trigonal bipyramid for all of these. Okay, but let's take a look now at our shapes, and this shows with lone pairs. And what I'm actually going to do here is I am going to put dots in here to show the lone pairs. Those are kind of hard to see. Let me try again. There we go. Okay, so this is where our lone pairs are. Okay, so let's see if we can take some look at some examples of that. I might not have everything I need here, but here's one. Okay, so hopefully you can see this. Okay, so see, I have 5 things on this, and one of them is a lone pair paddle. Okay, and now if you can kind of imagine that if this was on a surface, it would rock like a teeter-totter or a seesaw. Okay, whoa, let me see. See how this kind of rocks back and forth? And that's called seesaw, the shape. Okay, and that's this one here. Okay, and let me see if I have a T shape. I do not. I don't have a T shape, but if you were to have one that had 2 lone pairs on your trigonal bipyramid, you would have a T shape. And make sure that you look at this really closely. It's easy to mistake your T shape with, it's probably hard for you guys to see this. Okay, and this is a trigonal bipyramid here. Okay. So it's easy to mistake T-shape with trigonal planar, and they are very much not the same thing. In a T-shape, these are 90 degrees and 180 degrees like this, okay, instead of 60, 66, 120, 120, 120, like what we see before. Okay, now if you were to replace, if you would have 3 lone pairs and 2 items on your central atom, it's still trigonal bipyramid, and the shape, those lone pairs go in this on the center triangle like that, and you're actually left with a molecular shape that is linear. I am having technical difficulties. Hang on, I'm going to pause this and see what's going on. Okay, I was able to get out of my slides there. Okay, so I've basically gone through all of this. The section on chapter 9 is short. It's fairly simple. I'll answer questions about it. Just for that, make sure that you read the annotations file and look at the slides very closely for it. You do not have to do all of the OWL homework for chapter 9, just the parts that refer to what we did, though you're welcome to do all of them. That's fine too. It's not too onerous. It deals with hybridization and the combining of molecular orbitals. So I'm going to let you guys go ahead and read that because it's mostly a read concept. All right, I look forward to seeing you all in recitation and at your final one-on-one Zooms. Thanks.